All right, so this is our civil engineering research search engine. Um, and I'm Siddharth Basam. I don't know if we should say our names.
Where is he?
I'm Kareem.
I'm Josh.
Rich.
Okay, so
Alright.
introduction. So civil engineering was our one of our largest departments, so we limited the depth search to 10. And poor functionality leads to difficulty finding faculty research. So we wanted the search engine that can crawl the civil engineering faculty page uh, and index documents for retrieval and present relevant results from a subjective query.
So the first step of our search engine is crawling. So we start from the seed URL, which is the civil engineering page. And then with a crawler, we find target pages and we append them to our data storage until we reach the set number of target pages or all are explored. Um, so the target pages are identified if they have the features that the faculty pages have. So this is where students can find research papers. So the faculty pages will have divisions for info and one more, I forget right now. But this makes sure that the pages that are being returned are appropriate for the students.
As for the text transformation, we uh in order to make it indexable, we were able to first tokenize the text into individual words, then remove stop words such as like English pronouns and useless filler words, and then we lemmatized the text into their roots. And then finally, we filtered for the punctuation using regular expression. As for our index creation, our engine indexes the terms and from each faculty's accolades and publications, as well as their research interests. And we were able to pull that from our MongoDB database.
So for the rank function, essentially it just allows a user to enter a query, and then that's parsed to extract tokens. And and then the function just calculates the term frequency, the TF of each token in the query, and then uses to compute the TF IDF values for the query in relation to a list of documents. And then it compares the query TF IDF vectors against the pre-computed TF IDF vectors of the documents using cosine similarity. And then it just ranks the documents based on their similarity to the query and prints the cosine similarity scores for the top 5 most relevant documents. And so for pagination, we so given we have like 10 links, we'd want 5 pages or 5 links on each page. So if we have 10 links and 2 pages, so it just compares. So we just list the documents in the page according to that max page size. So 5 links fit in 1 page, and then with the remainder, if it's equal to or less than 5, then we just put it all in a second page, and if it's more, then we create a third page for the remainder. Yeah.
The difficulties that we faced are keeping track of the current URL in the DB, because if we strictly follow the pseudocode, then it's really easy to get the URL lost. So we lost the reference of the page with the content. So what we did was concatenating the URL at the very beginning of each HTML, so we can go back to it if we want. And the second one is duplicated URLs. Once we visited a page, there's actually a different format of the same link. And in the database, it will appear as two different entries of the same HTML content. The third one is wildly different fresh URL format. So a lot of the URLs are relative, and they could also be having different base URLs. So we have to try a lot of edge cases. And not all URLs have HTTPS, sometimes HTTP, and sometimes .com, .org, and .shtml. We spend a lot of time trying to figure that out. And wide variety of links. If we don't try to shorten the amount of pages that we can visit much more, then it'll go very far into the crawling process. It'll even go out of the cpp.edu bounds. And data types across libraries are not unified. And that made debugging a lot more difficult since we have to learn all the libraries and new methods as well.
All right. Nice.